of the Bayesian theorem. Okay. And this gives you a quantitative control on the deviation that appears in the series. So if you have a random variable, 0 meaning, let's say, variance sigma squared, and then the third moment, absolute value, the absolute third moment is rho, then these type of results tell you, if you look at the CDF of this quantity normalized, this is going to be the standard variation. 0 means subtracting divided by the standard deviation, which is sigma over n. This by CDF converts to normal, standard normal. If Fn is the CDF and then phi is the CDF of the standard normal, overall x, so this is basically the uniform control, premium over x is control like that. And so the deviation like goes like 1 over root n, assuming the threshold is finite, and so the constant turns out more as well. The c is you can see. So originally was 7 and all the it went all the way like now it's like below 0.0 475, let's say. So you can write something like that. Yeah, so like there are different variations, but the main idea is that the deviation like goes like 1 over root n. Because you get a sense of. And this is sort of the worst case. In the special cases, it could be better, but this is saying for any distribution with finite third moment, basically. This is the worst case found. And sort of this is optimal in the worst case in the sense that you can have faster than this generally overall possible distribution. So the distribution for which it goes like great. But there are cases, for example, you have Gaussian. Let's try to wrap this chapter up. We were discussing this idea of asymptotic normality, which we showed for the MLE, or actually we discussed for the MLE. So for the MLE, assuming consistency and regularity assumptions that went into Cramer-Rao, and assuming that the conditions of that asymptotic normality theorem holds, we have a convergence to distribution to normal asymptotic variance, which is 1 over the Fisher information, or asymptotic covariance, which is inverse efficient information matrix. And so we decided that this means MLE is asymptotically efficient. And then there was an example, another example of the application via the delta method that you can use to arrive at asymptotic normality results for estimators that can be written as basically plug-in estimators. So if I have an x bar, like well f, which is p squared, then the delta method allows me to just easily drive the asymptotic distribution, right? And then the asymptotic normality result of this form for that particular plugin. Maybe I'll come back and talk about some of the proofs. But yeah, so this was an example of a multivariate version, so you can apply it in a multivariate setting, and multivariate delta method would be a very powerful tool. This, for example, shows that we can drive asymptotic normality, an asymptotic normality result for the sample variance or the sample standard deviation by writing it as a function of this pair. So we did this last time. So what is left of this chapter is the use of asymptotic normality, which we have seen already. We've seen one of them, which is building asymptotic confidence intervals. The other one is simplifying the comparison of estimators. Okay, so basically, instead of comparing the risks of estimators, let's say I have two estimators which satisfy this type of asymptotic normality result. So I have a sequence of estimators, theta hat 1n, and then another sequence theta hat 2n, and I managed to prove kind of result like this for I equal 1 and 2. And you can see they're both consistent for mu theta. So this implies in itself that just as a point to point out, when I write something like this, if you show me something like this, I can use. This is a constant estimator of mu theta, right? So it implies, let's say I(n) converges as n goes to infinity in probability to mu theta. The reason being convergence distribution implies, so this implication is like implicit in that statement. The reason is if I, for example, give you root n Tn minus something, let's say theta converges to normal to 0, right? Sigma squared theta. This implies that root n Tn minus theta is big OP of 1. So if you remember, one of these results was that if something converges in distribution, then it's bounded in probability. Okay, we haven't used it much, but that's one of the results. And so you can imagine that I can manipulate these OPs. So this is equivalent to saying something like this is 1 over root n OP of 1. So now I have a sequence that converges to 0 and a sequence which is OP of 1. So this is going to be a little OP of 1. It's another property. So this is deterministically going to 0, but obviously it's also like little OP of 1. And so we have, if you have OP of 1 times a big OP of 1, then it's going to be OP of 1. Okay. And sometimes even people write this as, rather than little OP of 1, it's better because I can just write it as capital OP of 1 over root n. So this thing means it's a term such that if I divide by 1 over root n, then it's big OP of 1, which is just that. Sorry. Yeah, so this term, so when you say big OP of an, it means it's like xn is big OP of an if and only if I divide by an, this is big OP of 1. Okay, so this whole thing is a term such that when I divide by 1 over root n, it's OP of 1. You can immediately see, right? And something like this, you know, it's OP little OP of 1, but I actually so it gives you a rate. It's saying that it goes down at least like 1 over root n. Okay, so that's sort of true. So we have consistency, and you sometimes say root n consistency because Tn minus theta is OP of 1 over root n. So first we're consistent for the same parameter, where you can say asymptotically unbiased for mu theta. And then we have two different variances, let's say, okay. Similar to the finite sample case where when I had, for example, unbiased estimators of a certain parameter, I could compare the variances, and that would mean I am comparing the risks. Here, we can do the same. So they're sort of asymptotic unbiased, and compare the asymptotic variances, and this gives me some sort of a notion of comparison of the risks at infinity. It's not exactly comparing risk, but that's what people use these for. So I have this, this is basically replacing my entire risk at infinity. And so what I'm going to do is I'm going to compare the ratios of the variances. And these ratios of variances have some interesting meaning in this following sense. So if I assume that n is large, roughly speaking, theta hat in has variance sigma I theta squared over n. Okay, this is not exact, but it's a rough estimate. And so assuming this holds for both of them, then I can ask what is the ratio of the sample sizes that I need to achieve the same, or like what are the sample sizes that I need to achieve the same accuracy for both of them. So let's say I'm going to say I have n1 samples for estimator one. This is, let's say, the level of accuracy that I can achieve for that one, and I have n2 samples for the other one. This is the level of accuracy I can achieve for that one, and I set them equal. And then the asymptotic relative efficiency would be the ratio of these sample sizes, which you can see is just the ratio of the variances. So it tells you like basically relatively how much more samples you need. For example, theta hat 1 relative to theta hat 2 would be n2 over n1. As a relative efficiency of theta hat 1 to theta hat 2 would be n2 over n1. And if n2 is very large, let's say if n2 is twice n1, this would be 2. It means that theta 1 is twice as efficient. So you need twice more sample size for theta hat 2 to achieve the same performances. Theta hat 1. Okay. So this gives you like a natural way of comparing estimators. If you don't care about the sample size, you can just define it to be the ratio of the asymptotic variances. So ARE bigger than 1 is saying that theta hat 1 is better, so we prefer theta hat 1. Okay. So this is the notion of asymptotic relative efficiency you see in some of the lower problems. Basically, you just have to drive this asymptotic normality result and then compare the variance. Yes, is there questions? Okay, so let's maybe do an example. Suppose we have IID samples from a distribution Fx, or like density Fx, with mean being equal to median. The median is unique and is equal to the mean. Let's say, for example, Gaussian is like that, or some of the other continuous distributions are like that. So the parameter of interest is both the mean and the median of the distribution. And let's say the variance of the distribution is 1. We know that, for example, a good estimate of this parameter is the sample mean. So we have like x bar n, which is consistent. And also we have the sample median, which is going to be also consistent, although we haven't shown it. This is not an application of law of large numbers, but it's not hard to show that the sample median as n grows to infinity is going to converge to the true median in this case, which is going to be also the same as the true mean. So we have two candidate estimators that we want to compare. And so for the sample mean, obviously we know this CLT holds, so we have the asymptotic normality results. For the median, you can show the results like this, which we haven't shown, but for example, Keener does this in one of the, I think, chapters. If you check, just writing things down and basically brute force approach proves that the solution is good. There are more general techniques that apply, but this function, for example, is not continuous or anything. So we can't use continuous mapping theorem or like delta method, or like not like the traditional delta method at least doesn't work. Maybe functional delta method. So if you read asymptotic statistics by van der Waal, there are more advanced methods that can like maybe manipulate this without, but let's say traditionally you can do it by hand from first principles, start from scratch, prove that this conversion distribution to a normal mean 0 and this particular interesting asymptotic variance. So the asymptotic variance only depends on the value of the density at theta. Okay, how large the density is at theta. And so it's interesting. So if the density is very peaked at theta, the asymptotic variance is small. You could have like an example where the density is like peaked here and very low in the middle. So this is bad for the median. It's drive this to 0 and the median would be very confused. Okay, and you can think about that yourself. So the variance, the asymptotic variance tells you something about the performance of this, and then you take the ratio and the ratio would be, so the asymptotic relative efficiency of, let's say, the mean relative to the median, ARE of, say, x bar n relative to Zn is going to be 1, basically. Oh, sorry, the one goes there, and the asymptotic variance of the other one is 1/4. Basically, it would be like 1/4 fx theta squared. Okay, so that's for a general distribution, and then you can calculate this for example, Gaussian. You would have that phi of 0 is 1/2 and this is basically f of x at theta would be the same as like the standard normal at 0, which is 1/2 and so this quantity would be 4 times 1/2 which is going to be pi over 2. Um, 4 times 1/2 pi, so you get 2/pi, and then inverse of it, like inverse of it would be like pi over 2. 1.57. So for the Gaussian case, the mean is more efficient by a factor of 50% or 57%. You need 57% less samples. And so this is quite interesting. It doesn't depend on the particular value of the mean, right? Because you're evaluating the density at this point, and the mean is the same as evaluating a density of standard normal at 0. So it's like independent of theta is 1.75. For other distributions, it could be the other way around, right? And so if you assume things are Gaussian, it's better to estimate by the sample mean. But assuming that you have a heavy tail distribution, maybe things will change. So that's a nice example of asymptotic relative efficiency. Okay. Sounds good. Okay. Then you can do like a million of these for yourself in the homework problems and elsewhere. That's one example is good enough. The other one is the confidence intervals, which we already discussed. There's another use of asymptotic normality results. So to remind you what a confidence interval or a confidence set is, it's just a random set that contains a true parameter with high probability, right? So and a 1 minus alpha level confidence set is basically a set estimator. So it's a sorry, a single number takes x1 up to xn and random set, basically. Okay. And this random set we want to contain theta naught, assuming the solution, the true solution of theta naught, to contain theta naught, we probably will do this out at least. So here's an example, which is okay. So there so I'm not going to go over this much because most of you hopefully know about confidence intervals. They are often built by using pivots. There are things that are dependent on both. So here's an example of a pivot in the normal family. Things that depend both on the data and parameters, but distributions, whose distribution can vary or independent of the unknown parameter. So you form these because then you know the distribution of pivot, you can manipulate it with the probabilistic statement about the estimate. So this is an example of the so the theory is you know so you know these. I'm not going to spend too much time, but there is also like a trade-off between the size of the confidence and this coverage problem. And it's a probability that it contains the two parameters called the coverage problem. If I make it big, obviously I can make S to be the entire space. I can make the probability equal to 1, so if being equal to 1. But that's not good. So I want to make it small as possible without compromising this inequality. So the use of asymptotics is that this is hard. So in general, finding these pivots is hard, but I might be able to find as an asymptotic pivot, as we've seen before. So you might be able to satisfy this in the asymptotics. So an asymptotic 1 minus alpha low confidence interval will be again, a random set that contains two parameters following converges to one minus alpha. And these are much easier to achieve in practice. In particular, if you have an estimator which has this kind of asymptotic normality result, and if sigma is continuous, then it's not hard to show that Tn plus minus sigma squared Tn over n, if you take the root here, times this is the upper quantile of the normal distribution. This is going to be an asymptotic confidence interval double 1 minus alpha. The only thing that we need to like sort of argue is a little bit of continuous mapping theorem, a little bit of Slutsky. So you'd first argue that if I replace, basically, I don't know theta naught, so this asymptotic variance, I don't know. But I can estimate it by replacing Tn with theta naught, because that's a consistent estimate, and sigma is continuous. So by the continuous mapping theorem, this ratio converges to 1. And then I multiply both sides of this by the two sides of that. So this side multiplied by this ratio converges to normal times 1. And I believe, okay, so I have to maybe rearrange a little bit. So first we rewrite this as root n divided by sigma theta naught. The n minus theta naught converges in distribution to normal 0, 1. This is fairly easy because there's another application of Slutsky that is multiplied by dividing by 1 over root. So that should be sigma squared. 1 over root sigma squared theta naught. The application of Slutsky tells me that this is true. Then I multiply by this side is multiplied by that, this side is multiplied by 1. This is a valid application of the Slutsky because one of the converges to constant, the other to distribution. When you multiply, you basically effectively replace this sigma squared theta naught with this quantity. Okay, so that we conclude that that converges to a so this was converging to a normal 0, 1 by the above. When I multiply by this, it converges again to the normal 0, 1. And then I can rearrange. So I'll let you do the rearrangement. So the probability that this is bigger than or equal to this quantity is bigger than or equal to z alpha over 2 is converging to 1 minus alpha. Because this is the upper quantile with the Gaussian. So what I mean is, if you have a Gaussian, alpha over 2 is like z alpha over 2 is the place where alpha over 2 of the mass is above. Okay, so from this, you get that this quantity is bigger than alpha over 2 converges to 1 minus alpha because you get the two-sided version. The fact that here it's going to be it's going to be alpha. The other way, less than or equal to 0 alpha to be 1 minus alpha, and so rearrange and get that result. Okay. It's not something that we haven't seen before. Okay, just a little bit of manipulation of the asymptotic variance. A similar application of that idea to the MLE gives you a confidence interval for asymptotic confidence interval for the MLE, right? So we have this under regularity assumptions, the MLE data and is consistent root, and so this is called root and consistency, and I think that we know it. Root and times the deviation goes to normal 0 to 1. So an implication, as I mentioned, is that this is big OP of 1 over root n. This is called root inconsistency. Here is root inconsistent with this particular normality. So if I multiply both sides by root efficient information, I get that. Effectively, I can replace theta not with theta hat n, assuming I is continuous by the same kind of argument. And this leads to this sort of asymptotic confidence interval. Okay, same idea. We just divide by the square root of efficient information and divide. this is one example of how to do confidence interval for the MLE. There are other ways. Okay, this is not the only way. This is not the only thing that converges to a normal. Based on the MLE, we can compute another asymptotic period. For example, if you recall, so this is, for example, my log likelihood, and the Fisher information is there's something missing here. The second derivative of this evaluated with theta with a negative sign. So that's I can write it as double dot. So expectation of negative double dot theta. And so if I look at right, so this actually would be okay. So this slide needs a little bit of change, because this is the Fisher information of, this is going to be the Fisher information of the entire sample. Okay, so the Fisher information for one sample would be basically 1 over n. So this would be n times this would be n times one of these. So this would be expectation of negative L double dot theta. So if you recall, because we're in the IA sampling case, the Fisher information associated with the entire sample is n times 1. So the I that appears in the asymptotic results is 1 of the sources, really 1 over n times, this is the Fisher information of the entire sample. So this is really I theta of n. So in any case, it's that expectation of minus 1 over n ln double dot theta. So what this is saying is that this quantity inside is an unbiased estimator of the Fisher information. Okay, sometimes referred to as the empirical version of the Fisher information. And so this would converge by the law of large numbers. Actually, not okay. So this would converge by the law of large numbers. 1 over n L double dot, let's say theta naught, converges to I theta naught, because this is really an average. You can see that I do 1 over n double dot on this. It's an average, but the law of large number converges to the mean. So this is an unbiased and also consistent estimator of the true parameter. What I really want to do is replace this theta hat and theta naught with theta hat n, which I don't know, and also conclude. So this is by the law of large numbers. I want to do something like theta hat n, because theta hat n is also consistent. I want to conclude that this converges in as well to the Fisher information. This is tricky because theta hat n itself depends on this L n, and so there's dependence here. But by the same argument in the asymptotic normality theorem for the MLE, which we didn't go through, so this requires that stochastic equicontinuity. But assuming that that result goes true, this also goes true. And so this will converge in probability to I theta naught. And so I can, instead of using, let's say I theta hat n, which I used here, right? And I replace I theta naught with this. I can instead replace I theta naught with this, because this is also consistent. And so what I would get as a result is something like this. I multiply and sort of divide. So remember, this was the result. I multiply and divide by multiply by this, which is conversion to 1 in probability. And so the end result is I get something like this. The ends cancel out, these will cancel out. And so you end up with a confidence interval that looks like that. Okay, which doesn't require you to calculate the actual Fisher information. You just have the likelihood, and you take the derivative and evaluate the maximum likelihood. So the advantage is I don't need the closed form solution. Right? So this empirical version eventually itself like averages out to the Fisher information. The only tricky part is this piece that I mentioned, which well, let's see if you want to talk about. So if you go through the proof of that asymptotic normality, you'll see why this has to go to zero. Oh, sorry, why this would be true. That's one of the reasons why we impose that stochastic continuity. Well, in any case, so that's another way of doing it, right? Yeah.
What's the difference between theta naught and the other hat in this case?
Theta naught is the true parameter. Theta hat n is the MLE. Right. Yeah, so theta naught is not known. This is what I want to estimate. This is my DM, my MLE. I believe there are even more ways. I think Keener, he talks about another way of doing it. If I recall correctly, I'm not sure, but the other ways probably that we can think of. Basically, any other estimator of good estimator of efficient information, we can replace as long as it's consistent. Any questions? Okay, so last piece is this variance stabilizing transform. The idea is that we can use delta, and this is for I have some morality like this. I can apply the delta method and basically form a function of Tn. In the end, I really care about asymptotic confidence intervals for theta. I can build it based on like any function of theta, let's say, or like any reasonable function of theta. So suppose I apply a particular f to Tn. This is a continuous and differentiable. It's going to converge to f theta, and I can use the delta method to get an asymptotic result of this form. Then I'm going to do this. I'm going to set like choose f such that this variance, asymptotic variance is constant. So the advantage is now I have an estimator whose asymptotic variance is stabilized. It doesn't depend on the unknown parameter. So I don't have to worry about estimating the asymptotic variance. So in all these cases, the asymptotic variance depends on the unknown parameter. So you have to estimate it, multiply it. But if I do a transformation, that's another way of getting rid of this theta dependent variance. So if the transformation will have this property that makes this asymptotic variance of FTN constant is called variance stabilizing transform. So in order to do that, you just have to solve sort of a differential equation, right? Or it's like a simple differential equation. Just usually like you have a derivative and then you integrate, you get the function. So here's an example. You have the Poisson. Mean and variance are the same, equal to theta. That's the property of Poisson. If I see out the sample mean convergence, has this asymptotic normality result for it. When the asymptotic variance is this variance of the Poisson. This is just this field. And so how do I get rid of that theta? I perform this calculation. So f prime of theta squared times the asymptotic variance is theta has to be constant. Let's say I set it equal to 1, for example. I get f prime of theta should be 1 over root theta. That could be negative as well, but this is definitely like one of the solutions. And so f theta would be 1 over, I'm sorry, 2 root theta. If I differentiate this, I get like that. Plus some constant, I can ignore the constant. I just want one function, and that would work. So that's my variance stabilizing transform. By the delta method, if I apply it, I get this result. 2 root x bar and minus root theta is like that. So because this is normal, we know that the probability that 2 root and root x bar n minus root theta is less than or equal to z alpha over 2 is going to 1 minus alpha. Okay, if you rearrange this, you get a bound like that. Okay, it's just saying that root theta is in this interval. Okay, so you get the confidence interval for root theta, which is fine. Okay, comparing with the standard as a target confidence interval for theta. This is the one based on x bar n, and whether one is better than the other, I'll let you decide. No good answer here, but this gives you a different way of constructing confidence intervals. Okay. Sounds good. Okay, so this concludes this chapter. So let's see if I want to, any questions? Maybe say a few words about the proofs. Usually this is the lecture we start talking about hypothesis testing, so I don't want to completely talk about the proofs, but maybe, so there's a consistency proof. Maybe I just comment on these proofs rather quickly. So the first one that we skipped was this proof of consistency, which is a very general proof. It's saying that if you have a random sequence of random functions that converges to M, and if you take the argmax, if the sequence converges uniformly in probability, and this other condition, which is roughly equivalent to saying that M has a unique maximum of theta naught. If these two conditions are satisfied, then theta is consistent. The main idea here is you write down the so-called basic inequality, because theta hat n is the maximizer for the Mn, and theta naught is not. It's just a feasible solution in parameter space. The value of theta naught should be less than theta hat. So that's called the basic inequality, and then you can rearrange it like that, and then you try to construct the deviation from the mean, or the target function. So you add and subtract m theta hat n and m theta naught. Okay, so you add and subtract these. So this inequality and these are the same. I just added and subtracted this. These blue and red pairs, and the way I rearranged it, this side contains this target function, so non-random linear. And this side contains the deviations of mn minus m at theta hat and mn minus m at theta naught. Okay, and both of these are controlled by the suit norm, because the mn minus m infinity is the maximum deviation among all possible thetas. So this is one particular theta. There's another particular theta. So both are contained by, or like bounded by this. And the key point here is that this one is easy to control, because let's say in our case, CLT would guarantee, sorry, the law of large numbers guarantee this, because we're doing it with single theta naught. This is the tricky part, because theta hat n depends on mn, because it's a maximizer of mn. So that's one of these quantities which is difficult to control, and the uniform control that we have allows us to upper bound this by this quantity, which we know converges to zero. Okay, so that the uniform convergence is important to deal with this term. Once I get that, I have proven that this by assumption goes to zero. Probably I've proven that basically theta hat and converges to theta naught in this M metric in this sense. M is sort of a metric, because by assumption theta naught is a maximizer, so this is going to be bigger than or equal to zero. So it's sort of a kind of distance. But then you can use this inequality, which I'm not going to go over. So you can do it. So this you can go over. Sort of gives you that this is bounded by some function of v of theta naught and theta hat n. So there's another function of let's say eta, something like that, or eta inverse, maybe eta inverse. I'll let you figure this out. So there's this function gamma of distance. So if this is going to zero, some other function of the distance goes to zero because of this property. And look at that function. Let's say this is linear, for example, this forces distance to go to zero. But this condition allows you to translate deviations in M to deviations in the distance. What it's saying is that if this is close to that, then theta hat n can't be too much outside theta naught. Because if you're very outside, then the value of n is going to be very small compared to this. So if this is approaching that, then it has to be the ball of radius close, basically close to theta naught. So this part is a technical part that you can figure out. But the main part is this basic equality followed by the uniform convergence assumption. Okay. The same team, any questions? It's a little fast, but if you go through it and then you have questions, maybe last lecture we can go over it as well. The same idea applies when you start doing okay, so this is stochastic equicontinuity. You can see well, it's a while. There's a line. Goes all the way around the globe. Okay. Now, all right. Stop. Okay. That's sort of the kind of result that we're going to use. So stochastic equicontinuity, if you go back, the main idea is if I have a sequence that converges to theta naught, and then I have something like that. You saw that this was appearing there, and theta hat and minus and then theta naught. Let's say if I have something like that, then I can control it by just applying theta and theta naught. So this is used the same in this proof. So in asymptotic normality, the idea is actually there is this part that we didn't talk about. There is this asymptotic expansion of the MLE in terms of the score function. So okay, not the score function, but in the case of the MLE, this would be the score function. So remember this m theta. In the case of MLE, the log theta. And so this is the score function, the root n times the score function. So this gives you a nice asymptotic expansion. So that's what we prove that root n times the MLE minus the naught is this. This is the leading pair plus something which is OPO1. And if you go back to the slide that lists these properties, if I have a sequence that converges. I have a sequence, another sequence whose difference is OPO1, and this converges to distribution in distribution something. And this thing converges in distribution because this is by CLT. And so we know that the score function or this thing has zero mean. So by the CLT root n times 1 over n summation I from 1 to n m double dot xi minus 0, because that's the mean, converges into normal 0, and the covariance matrix of this, which we define as v theta naught, if you recall. So that's the covariance. Sorry, this is going to converge to S theta naught. That's the covariance matrix of this. So this has a CLT. And so v theta negative inverse times this will have this normality result, because this is another application continuous mapping. Combining this result, which is so this is the CLT. If I apply v theta naught here by continuous mapping, I get v theta naught inverse here. And so v theta naught inverse times the normal is another normal with the variance, like covariance, like okay. This is just a linear transformation of something that converges to a multivariate normal. And so the only change is that this is also going to be multivariate normal with the covariance, which means like this. Okay. Is this sort of clear? So this is not the difficult part. Okay, so this is the result that we proved, and it's good to remember that the MLE has an expansion, or the asymptotic expansion in terms of the score function. Once you prove this, and because this is true, that's this statement here. So this is basically that. So this is true, and this is true, then this result follows from continuous mapping theorem and that property. So how do we prove this? That's what I want to say. So the way you prove it is, again, it's like a basic inequality argument, but it's like a differential basic inequality. So theta hat is a maximizer of Mn, and we know that theta naught is in the interior. So it's sufficiently large and it's going to be in the interior. And so we're maximizing Mn. And we know that the maximizer is in the interior of the domain, so it has the derivative has advantage. And so this is my basic inequality or basic equality, basically. So that's the starting point. Then you do the Taylor expansion. All of these asymptotic, classical asymptotic results follow by applying Taylor expansion. So you do a Taylor expansion of Mn around Mn dot. So the derivative. This is basically the score function. And you think of the MRV around theta naught. So you get this deviation is Mn double dot theta tilde n, a point in the interval, so the line segment that connects these two, not necessarily the interval, but it could be multivariate. So this notation is the line segment. So line segment connecting these two. This is the second derivative of the Hessian times theta hat and then theta naught. So this is Taylor expansion with Lagrange, not Lagrange, but like the form of Taylor expansion with remain like precise Taylor expansion. Okay, or you can say it's just a mean value theorem in this sense. I believe it's mean value theorem. But first order Taylor expansion, and then what I get is this is 0 by the above, and this is so Mn is like, remember, that is this our score function, which when I multiply by root n, we know that root n times this by CLT converges to normal 0 as theta naught. This is the CLT. So if I rearrange, I get I get something like this. Okay, so I get rearrange that equation. So this is 0. And if I multiply by root n, I get root n theta at n minus theta naught, m double dot n theta tilde n inverse, and then root n negative m n theta naught. So this by CLT is controlled. The only problem with this guy, and this is where we use that stochastic continuity. So this assumption is a similar uniform control. Because theta hat n is converging to theta naught, theta tilde is in between theta naught and theta hat, and so that also converges. So then I can evaluate this at theta and tilde that converges, or that can be replaced by this assumption, or by this result. Sorry. Sorry. So this is like this can be replaced with this plus OPO1. That's the stochastic equivalent. And so this is an average. We know that by the law of large numbers it converges to the expectation. The expectation we call the theta naught. So this, when I consider this, this is v theta naught plus OP of 1. And this is that quantity, this thing, plus OP of 1 by the Slutsky order, just basically. And then I think it's like one of the other results. It's very simple. So this conversion probability keeps counting, and the difference is OP of 1 and converts to the same thing. Okay, so this result results in this quantity being v theta naught plus OP of 1. And then I use the continuous vacuum theorem, the inverse of it would be v theta naught inverse plus OP of 1. So in the end, I get a result like this. I can replace it with v theta naught inverse plus OP of 1. And this is by CLT, this converges to Yeah, okay, so I need the root n here. So I get v theta naught inverse plus OP of 1. And this thing is converging to a normal. If you replace this here, you get so there's v theta naught times that plus OP of 1 times that. So that's the statement here. So this part is what we needed. This is we go back to the main theorem. This is the delta n. And this is going to be going to 0 because again, by CLT, this is converging in this distribution. So this is big OP of 1. And this is little OP of 1. So the product goes to 0. So there's little OP of 1. So this entire thing is like just a nice application of all these results. It was a little bit quick, but everything you should be able to follow, except a little bit of hiccup here, which we use that heavy machinery. Okay. So we use the heavy machinery of stochastic equicontinuity to replace so this double randomness, which is randomness here, which is basically over there. So that's the stochastic equicontinuity assumption. And exactly this procedure is what allows me later in that confidence interval. So this business that we had here, if you remember. So sort of here, I can replace this minus 1 over n theta hat in here with theta naught, and then this is by large number converges to the alpha. So that's exactly what that step is doing. Okay, so I encourage you to go through this argument for yourself. And if there was anything unclear, so it's like spelled out everything, like each step uses one particular property. And there's nothing fancy here. And in the end, what you get is this asymptotic expansion. And this has so this is the scale of the score function. And by CLT converges to normal, and we already saw that. The rest follows. Okay, sounds good. Okay, given the short amount of time that we had, I think it's good enough to just start from both of these results start from some optimality condition, either differential or like inequality. In that case, in both cases, there is some sort of uniform control that we go, like we use to get rid of this double independence. So that's, I think, the high the high level takeaway points that you want to take away. The delta method I'm going to skip is very similar. It's just the Taylor expansion. So you do the Taylor expansion of f around theta, and then argue that the remainder sort of is O1. Very similar idea. Okay, sounds good. I'm going to talk about hypothesis testing to have like a complete picture. Most of the course we have been talking about basically estimation, point estimation, so-called point estimation, or a little bit of interval estimation, confidence intervals. Hypothesis testing is, in the simplest form, a simpler problem. So you have parameter space. Again, let's say you have the decision theoretic framework, and the parameter space is now, let's say, either binary 0, 1. That's like simple hypothesis testing. Or if it's a little more complicated, which is usually, it's partitioned into two disjoint sets. And we just care about whether the parameter belongs to theta. Like, you want to determine whether the parameter belongs to one of these two sets. I don't want to pin down the exact parameter. I just want to know whether it's in theta naught or theta 1. Okay. So the parameter space is big. I just want to know whether it lies in this portion or in that portion. For example, the common example is like you have a like scalar parameter. You want to know whether it's non-zero or 0. Okay, so this is like real line. Just take one point out. This everything else would be, let's say, omega 1. Null would be like theta is 0. So oftentimes, like you have a model, this would be sort of called H naught. This would be H1 usually. This is the null hypothesis. The null theta is 0. The alternative is that it's non-zero. So everything null. And doesn't have to be like that. So for example, this could be like this is bigger than or equal to 0, this is less than 0. Or it could be the null is the alternative. So null and alternative are sort of a little bit made up. Okay, so which one you want to call null is up to you, but they will play an asymmetric role in Neyman-Pearson framework. Oftentimes the null is the default. This is our default assumption, and then this is something interesting. The alternative is if you reject the status quo. But from the theory perspective, it's sort of they play up to a certain point they play a symmetric role. You treat them differently. Okay, so the goal is to find a test, which is a decision rule that maps your data into one of these two choices. So because I just want to determine which one, I can just say 0 or 1. Okay, so that's my decision. And so the output of a test would be a binary thing. So I would say I'll observe X from P theta, and then I output 1 or 0. So this means that theta belongs to, like, means theta belongs to omega 1. This means that theta belongs to omega 0. Okay, so binary hypothesis testing, which is what we're looking at, just reduces to defining an estimator. Sorry, a decision rule that has this binary output. So a very simple way of doing it is to form an estimator for theta. And I know that what omega 1 and omega naught are. So these are unknown, they're known to us. So this is a particular decision rule that can act as a test, right? So if theta hat belongs to omega 1, I output 1. If not, I output 0. So this is a reasonable test. It's a form of a plug-in test, but oftentimes the general principle in the statistic is that if you care about a particular parameter, it's better to estimate that parameter directly rather than estimate something bigger and then try to reduce it. Because when I try to estimate the entire data, it would be more variable. The estimator would be more variable, and this is not necessarily the best way to reduce. Okay, maybe there is like a more efficient way of just answering the actual question. So that's the goal. So what is the best way to decide this dichotomy? Okay. Is that sort of clear? Okay, so to have some sort of head start for the next lecture, let's review some definitions. So we have a null hypothesis, as I mentioned, and an alternative hypothesis. These are basically statements of this form theta belongs to omega naught, theta belongs to omega 1. A non-random test can be specified with a critical region. So instead of specifying a binary function, I can just say, like, just specify the set of x's that it maps to 1. That's equivalent. Okay, so basically this is the S is the set of x's that delta x maps to 1. Or alternatively, I pick up the set S and just define delta x as the indicator x belongs to S. So this set S is called the critical region. So specifying a test is equivalently done by specifying the critical region. So if delta x is 1, we have accepted H1. Some people don't like it, so they rejected H1, H naught. I'm not going to worry too much about that. Just we either declare H1 or H naught. Okay. So the power of the test, which is really important, is the probability under the true parameter that X belongs to the critical region. And because this test is delta is an indicator, it's also the expectation of delta x. Okay, so this is hopefully clear. And what is an ideal test or what is an ideal power? An ideal power looks like this. So you want to be 1 if theta is in the alternative piece of the parameter space and 0 otherwise. Okay. So this is the the ideal test. So if this is omega 1, this is omega naught, this is omega 1. So you want to jump from 0 here to all the way like 1 here. That's the ideal test, like power of a test, power of the ideal test. But that's not often achievable because these are conflicting. So being very close to 1 here often in conflict with being 0 here. So one way to make this, for example, 1 is to make the critical region be the entire space. So this is going to be always that. The other way I can take it empty. So it's always going to be 0. So always 0 or always 1 is easy, but the sharp transition is not easy because as I change the set, I'm going to manipulate both of these probabilities. So I can't like fix one, control the other. So for that reason, people try to settle for trade-off. And the way that classically people try to settle this trade-off is to say, okay, I'm gonna allow myself to be like alpha bad. So I'm not gonna require that I'm gonna be 0 here. I'll let you be at most alpha. I'm gonna give you the budget of alpha. So be as you can be as bad as alpha, but not more. The subject to this, how high can you guarantee the other portion? So the test could like do something like this, and then if it just jumps to like something very close to 1 here, that would be very nice. Okay, and so we define the significance of all the tests to be the maximum, the worst case of this power over the null, so alpha, and the smallest value beta, this power, this is called the power function. So the power function, the smallest value of omega 1 is really called the power of this. Okay. The smallest over the alternative, the maximum over the no. So I want this to be small and I want this to be high. And the way that sort of classically people work this out in the frequencies camp is why I left the Pearson framework. I'm gonna give you an upper bound here. I'll let you the significance level of test, let's say, can be bounded by 0.05. Find me a test for which alpha is below this, but maximize beta for me. Okay, so maximize beta of the test, let's say, subject to the alpha of the test being less than 0.05. Well, that's the name of the Pearson framework. It solves a constraint optimization problem. Okay. And in order, is it sort of clear? So that's the goal. Try to give you a budget of, you can have it like alpha. You can say alpha of delta if you want, because they all depend on delta. So that's a maximize overall delta, basically. Alpha of delta, beta of delta. So one thing to do before we go there, it turns out that to solve this in general, we need to extend, enlarge the class of tests or decision rules to randomized decision rules, which we have come across before. So randomized test would be, instead of producing exactly 0 or 1, basically gives you the probability of deciding 1 or 0. Okay, so then you would flip a coin. So delta x in the randomized decision rule would be basically the probability of accepting H1 given x equal to x. So if something is 0 to 1, but then using the power property, it's easy to see that the probability of acceptance would be the expectation. Okay, so this formula, the second one, always works even for randomized rules. So the expectation of this over x would be the probability of accepting H1 or rejecting them all. So we enlarge the class to these randomized tests. And so let me maybe just give you the punchline and then talk about it. So today we work with the simple hypothesis testing first. So we just have two like singleton sets, omega naught and theta naught, omega 1 and theta 1. So Naylor-Pearson criteria is like this. So because we're minimizing, sorry, maximizing the smallest, the inference soup go away here, right? So because there's just one element, so this would be just beta of theta naught here, this would be beta of theta 1 here, okay? So that's the power function at theta naught, that's the power of this. This is the significance level of the test. So I want to minimize, so maximize the power subject to the constraint on the significance level. And if you write this down, this is a linear programming problem. And you can use like a Lagrange multiplier to solve it, which we'll do hopefully next time. And it turns out the solution is something like this. The solution is called the most powerful test at significance level alpha. And it's achieved by the likelihood ratio test. So what we do is we form the likelihood ratio, p theta 1 of x divided p theta naught of x, and then compare this with the threshold. If this likelihood ratio is bigger than tau, the hypothesis 1 is true. If it's 0, obviously if it's 0, it's like null is true. Right? We reject the null, we don't reject them. And this piece here is the randomization part. So if the likelihood ratio never is equal to that particular threshold that we need to do, so things are like distributions are continuous, then this part is not there, so you don't have to worry about it. If the probability you want, you don't never see this. But if the distribution has sort of like point massive and stuff, it could be positive probability that the likelihood ratio ends up hitting the threshold. And in that case, we randomize. We have a gamma here. It is saying if the likelihood ratio is equal to tau, just put the correlative probability. And then decide based on that. So this is probability of acceptance. So another way of writing this is like that. If the likelihood ratio is bigger than t, it's 1. If it's less than t, it's 0. If it's equal to t, flip a coin if it's all. Okay, so I think we're done for today. So I'm going to stop here, and next time hopefully come back, talk about a little bit about the proof and applications, and try to wrap up. Sounds good? That's fine. Okay, thank you guys. Next time.